All right. So last time we talked about operators and linear operators, and one of your homework was to uh, show that C is not a linear operator. Okay, so let me show you the proof for that. You're going to say, all right, so if I were to say C operating on a sum of functions f and g, condition one that must be satisfied is that it must be equal to C operating on f plus C operating on g, right? So is that equal? Well, what do you do? If you have C operating on anything, f can be anything, right? So you just take the complex conjugate for whatever that thing is. So this is just going to be f plus g star. But if you want to take the complex conjugate of anything, you just take the complex conjugate of everything that's in there. Anything in there that's got an I, you replace by negative I. But since this is generic, you don't know this f right here might have some i's in it. So basically, all you have to do is you're going to take the complex conjugate of that is you take the complex conjugate of f and you take the complex conjugate of g. Okay? But complex conjugate of f is just what? CF, right? And the complex conjugate of g is just C hat g. So this condition is satisfied. So if it's not a linear operator, it must be the second condition that's not satisfied. So let's take a look at the second condition. C operating on a constant times function f. The second condition that must be satisfied is that you should just be able to pull out that constant. So that's going to be equal to C times C hat operating on f. So let's do that. So this is going to be equal to C star F star, right? And every expression you have in there, you just star it. Okay, to make it more clear, more step by step, you say this is going to be CF star. But CF star is just C star F star. Okay, but what is F star? So that's going to be C star, but F star is just C hat F. Okay? So these two are not the same. So generally, this statement, these are not equal unless C is equal to C star. But we're not insisting that C be a real number. C can be any number, any constant. So a complex number is a constant. Okay? So that means this condition is not satisfied if C is not real, if the constant is not real. Let's take a look at parity operators now. Okay. A parity operator, pi hat here, okay, is an example of what's called a replacement type of operator. Okay, so the rule is there's something in your function, replace it with something else. Okay, so replacement type operators are generally can be shown to be linear operators. So let's show that the parity operator is a linear operator. What the parity operator does is if you apply it on a function of x, you simply replace every instance of x by negative x. Let me just illustrate. If I were to do parity operator on 3x cubed plus 2x squared, what would that give me based on that definition? I see an x, I replace by negative x, so that's going to be 3 times negative x cubed plus 2 times, I see an x, I replace by negative x, so 2 times negative x squared. So that gives me negative 3x cubed plus 2x squared. Okay, so that's what the parity operator does, right? So let's see if the parity operator is a linear operator. So let's do phi hat operating on f of x plus g of x. Is that equal to, let me get rid of this. Is that equal to f a parity operator operating on f of x plus the parity operator operating on g of x. Okay, so what's the rule? I see an x replaced by negative x. So if I start with the left side, I see an x, I replace it by negative x. So that's f of negative x. And I see an x here. What do I do? Replaced by negative x. But what is f of negative x? That's the same thing as a parity operator operating on f of x, right? And what is g of x? G of negative x. That's just the parity operator operating on g of x. So this expression is the same thing as that. So the answer is yes. Okay, so what about the second condition? That should be straightforward. Parity operator operating on a constant times a function of x. Is that equal to a constant times the parity operator operating on f of x? Is it? Should be. So what do I do here? Constant times, where I see an x, I replace it by negative x. But what is f of negative x? Parity operator operating on f of x, and that is what we want to show, right? So, and that's the same thing as that. Okay. So on to the next one, next example. A multiplicative operator is just an operator that multiplies the function by something. Okay? All it does to the function is it multiplies it by something. It could be a function of the variable that the operator depends on. It can be a number. Like, for example, if I define a hat f is equal to x squared f. All it does is whatever the function f is, I multiply it by x squared. So if I would do what's a hat operating on 2x, it's going to be x squared times 2x, so it's going to be 2x. Okay. So that's a multiplicative operator. So is a multiplicative operator a linear operator? And the answer there is yes, and that's going to be homework. Okay, so that's going to be your next homework. Show that it is a linear operator. Okay. Now, there are other multiplicative operators you might encounter. For example, like something like a hat. Let me use another operator. Let's say, find another letter. Let's not keep using a. E hat operating on f is just f. Is e hat a multiplicative operator? All it does is it multiplies the function by 1, right? So it's a multiplicative operator. So e hat is a linear operator. Okay. E hat would be an example of what's called an identity operator. You can also represent it a more descriptive way of representing it is calling it 1 hat. Operating on f gives you 1 times f. Okay. What if I say n hat operating on f gives me 0? Is that a multiplicative operator? It multiplies the function by 0. So that's called the null operator. Another way you can represent it is 0 hat f equals 0. Okay. So that's your null operator. And this is your identity operator. Prove that products of 2 linear operators is also a linear operator. This is where you apply the rule for multiplying operators. So let's say a hat and b hat. So you're going to assume a hat and b hat are linear, right? Those are the 2 operators we're going to use. So what do we need to show? A hat, b hat operating on f plus g. Does that equal a hat, b hat, f? plus A hat B hat G. That's condition 1. And condition number 2, A hat B hat constant times F is that equal to constant times A hat B hat F. Okay? So that should be true, because I'm asking you to prove that that's true. Right? So let's see. Let's start with the first one. A hat B hat F plus G. What do you do? When you're multiplying operators, what do? You apply the rightmost operator first, right? Since B hat is a linear operator, what does this tell me? I can write A hat. I can distribute my B because B is a linear operator. So I can say that's BF plus BG, right? Because B is a linear operator. Now A is also a linear operator, so that means I can distribute A to that. This is just another function, and that's just another function, remember? Okay, so now I can say this must be equal to A hat B hat F plus A hat B hat G. Okay? And if I know that A hat B, that this is A hat B hat F, I know multiplication. This is the same thing as A hat B hat F, and this is A hat B hat G. Okay, I'm actually missing a step here in the proof. I should have said this is A hat times B hat operating on F operating on B hat operating on F plus G. I missed a step there. So this is the step I should have done first and then there. Okay? That first step is the definition of what an operator multiplication is. Alright, so we've proven the first case, the first condition. What about the second condition? A hat B hat operating on C times F, where C is a constant. So multiplication means apply B first, right? So that's going to be A hat operating on the result of B hat operating on CF. What is B hat operating on CF? Since B is a linear operator, I can move my constant out, so that's going to be equal to C times B hat F. And B hat F is just another function, right? So that's just like C times function G, right? So now I can move my, since A is also a linear operator, I can move my C outside. And so this is just going to be equal to C times A hat operating on B hat F. Okay, so you just do it step by step by step. Don't skip any steps, okay? Apply the definitions. And then what do you do next? This is just going to be C times A hat B hat F. So that's the proof. So you have a product of two linear operators. The result is also a linear operator. Okay. Got it? Okay. Homework number 2. Sum of two linear operators is also a linear operator. So if A hat and B hat are, if A hat and B hat are both linear operators, then the sum of A hat plus B hat is also a linear operator. I need a proof of that. Okay? So what are the conditions we need to satisfy? If you apply this on F plus G, that gives you A hat plus B hat F plus A hat plus B hat G, right? And the second condition you need to satisfy to prove is that A hat plus B hat operating on constant times F is equal to constant times a hat plus b hat operating on f. Okay? So that's what you need to prove. Now, things you need to know. What? Definition of the sum of two operators. If you have two operators operating on a function, what do you get? You can distribute your operator, right? That's true whether or not I'm sorry. Yeah, that's true whether or not A and B are linear, right? Sum of operators. So that should help you out. All right, so let's move on to eigenfunctions and eigenvalues. If the application of operator A on a function f yields a constant times the original function, so A here is a constant, okay, then we say that this function f is an eigenfunction of operator A. Okay? And this little a, this constant that comes out, is called the eigenvalue corresponding to that eigenfunction. Okay, so for every eigenfunction, there's a corresponding number, and that number is called the eigenvalue. That's the number that comes out when you operate on the function, okay, on the eigenfunction. So let's show that for example, show that e to the 3x is an eigenfunction of a, and determine the eigenvalue if we define operator a this way. So operator a simply takes the derivative of the function you're applying it on, okay? So let's see. If this is our definition of operator a hat operating on 3x would be equal to what? Derivative with respect to x of, oops, that's not 3x, e to the 3x, right? We're doing e to the 3x. So that's the derivative of e to the 3x with respect to x. What's the derivative of e to the 3x? 3e to the 3x. Okay, so you can see this is your function f, and this is your function f, and this is your constant a. Let's call that a. So you say a equals 3. What do you call a? This is the eigenvalue that corresponds to this particular eigenfunction. And so we've proven that here that when you operate a on e to the 3x, you get back a constant times the original function. So e to the 3x we say is an eigenfunction. Right? So is sine x an eigenfunction of operator a? Okay, what is a hat sine x? That's the derivative with respect to x of sine x. What's the derivative of sine x? Cosine x. Is that equal to a constant times sine x? Can you write cosine x equals a constant times sine x for any x? There's no constant that you can multiply with sine x to get cosine x for every possible value of x. So that's not true. So you say the answer is, for this first one, no, right? Sine x is not an eigenfunction of operator a. What about a squared? What do we mean when we say a squared? Operator a squared, okay, operating on function f, that's the same thing as a operator applied twice, okay? So what happens if we take a squared, operate that on sine x? That's a hat sine x. So this is a hat. Apply the first operator. What do you get? Second derivative with respect to x of sine x. So that gives you a hat cosine x. And what does the a operator do? Takes the derivative of cosine x in this case. What's the derivative of cosine x? Negative sine x. So you're saying then that a squared of sine x, operating on sine x, gives you back negative sine x. So is sine x an eigenfunction? Is that equal to a constant times sine x, the original function? Yes, right? And what's the eigenvalue? Equals negative 1. Okay, so that's what eigenfunction and eigenvalue means. So is cosine x an eigenfunction of the parity operator? Remember your parity operator? Every time you see an x, replace it by negative x. Question?
I didn't ask what the eigenfunction was at the last one.
The eigenfunction from the last one is negative 1. See, it gives you back negative sine x. The eigenfunction is sine x, I'm sorry. And the eigenvalue is negative 1. Because negative sine x is just negative 1 times sine x. Alright. Cosine x, is that an eigenfunction of the parity operator? Parity operator operating on cosine x gives you what? Every time I see an x, I replace with negative x, so that gives me cosine of negative x. But cosine of negative x is just cosine x. It's an even function, right? So the answer is yes. What's the eigenvalue? Eigenvalue is plus 1, right? So an even function, in fact, any even function is going to be an eigenfunction of the parity operator. If I do pi squared of 2x squared, what would that give me? 2 times negative x squared, and that will give me 2x squared. So eigenvalue is 1. Okay? What if you have an odd function? That's an example of an odd function. Sine x is an odd function, right? That would give parity operator operating on sine x would give you sine of negative x. So what is sine of negative x? Negative sine x. So is sine x an eigenfunction? Yes. And what's the eigenvalue? In this case, the eigenvalue is negative 1. So an odd function is an eigenfunction with an eigenvalue of negative 1. An even function is also an eigenfunction of a parity operator with an eigenvalue of plus 1. Okay? What about sine x plus cosine x? Is that an eigenfunction of the parity operator? And that's going to give you what? Sine of negative x plus cosine of negative x. So that's negative of sine x plus cosine x. Is that an eigenfunction? No. It's not equal to a constant times the original function, sine x plus cosine x. Okay? So it's not an eigenfunction. So if you have, anytime you take combinations, this is what's called a linear combination. You have to take a linear combination when you're adding these functions. If you take a linear combination of odd and even functions, we say they're not eigenfunctions of the parity operator. So you say odd functions have definite parity. Okay, if the eigenvalue, you can say it's got an even part. We say symmetric if the eigenvalue is plus 1. It's anti-symmetric if the eigenvalue is negative 1. Okay, so even function symmetric, odd function anti-symmetric. Eigenvalue plus 1 if it's symmetric, eigenvalue is negative 1 if it's anti-symmetric. But if it's not an even or an odd function, it's a combination of both, then you'll end up with a function that is not an eigenfunction of the parity operator. What about this one? Pi operating on sine x over cosine x. Is sine x over cosine x, which is really tangent x, right? Is that an eigenfunction? Yes, because this is going to be equal to negative of sine x over cosine x, right? So tangent x is an odd function. An odd function divided by an even function is still an odd function. What about sine x times cosine x? An odd function times an even function is also an odd function. This is going to be what? Negative of sine x cosine x. Okay? What about x plus sine x? Question?
You wouldn't change both x to negative?
Yeah, if you did,
And then negative times negative.
this is going to be sine of negative x times cosine of negative x, right? But cosine of negative x is just cosine x, and sine of negative x is just negative sine x. What about x plus sine x? Yes, this is an odd function plus an odd function. So if you're adding odd functions, you get an odd function. If you're adding even functions, you get an even function. It's when you add or subtract odd and even functions that you get something that no longer has a definite parity. So we say odd and even functions have definite parity. Okay. So let's talk now about degenerate eigenfunctions. What do we mean by the degenerate eigenfunctions? Well, if two eigenfunctions have the same eigenvalue, okay, then we say that they are degenerate. So here's an example, simple example here. Which of the three eigenfunctions of A are degenerate? First of all, why do we say that f1, f2, and f3 are eigenfunctions of operator A? Because when you applied operator A on those functions, you get back a constant, right? So what is the eigenvalue corresponding to eigenfunction f1? 2. What's the eigenvalue corresponding to eigenfunction f2? 2. Since f1 and f2 have the same eigenvalue, then we say f1 and f2 are degenerate eigenfunctions. Okay? So we say f1 and f2 are degenerate. F1 and f3 are, they're not degenerate. F2 and f3 are not degenerate. That's what we mean by degenerate eigenfunctions. These are eigenfunctions that have the same eigenvalue. Okay. Now let's prove that any linear combination of degenerate eigenfunctions of a linear operator is also an eigenfunction with the same eigenvalue. So let's understand what we mean by linear combination. If I have two functions, f1 and f2, okay? A linear combination of f1 and f2 is a function that is a constant times f1 plus another constant times f2. So c1 f1 plus c2 f2, where c1 and c2 can be any constants. So, for example, 3f1 plus 4f2, that's a linear combination. Okay? So what's our c1 here? 3, and c2 is, okay, so let's just say our functions are functions of x. Is x f1 plus 2f2 a linear combination? No, because x is not a constant. Okay, so that's not a linear combination, assuming x is a variable that f depends on, the functions depend on. So a linear combination of two functions means constant times function 1 plus constant times function 2. Okay? If we have three functions, what's a linear combination of those three functions? Constant times function 1 plus constant times function number 2 plus constant times function number 3. So that's what we mean by a linear combination. So what are we trying to prove here then? We're saying that if you have two we're just going to prove this for two eigenfunctions. You can generalize this later to more than two eigenfunctions. So let's say, what if we say function g is equal to c1 f1 plus, so let g equal c1 f1 plus c2 f2. So that's a linear combination. And we're going to let f1 and f2 be eigenfunctions of operator A. Okay, so we're going to assume that A f1 gives you some eigenvalue a1 f1. A1 is a constant, okay? The eigenvalue for f1. And we're going to say function f2 is also an eigenfunction with an eigenvalue equal to a2 f2. So this is a2 is the eigenvalue for f2. Okay. If f1 and f2 are degenerate, what can be said about a1 and a2? They're the same, right? So we're going to say since f1 and f2 are degenerate, we know that a1 is equal to a2. Okay? So, what am I trying to prove then? That a hat operating on G gives me back a constant times G, right? That's what I'm trying to prove, because G is a linear combination of two degenerate eigenfunctions. And what is that constant I'm going to get? It's going to be A1 or A2. A1 and A2 are the same, right? So this is what I'm trying to prove then. So let's see if we can prove that. What's A hat operating on G? What's our definition? What would you say G was? Constant times F1 plus another constant times F2, right? All right, so what is that? A is a linear operator. What can I do with A? I can distribute it, and I can pull out constants from it, right? So this is going to be A hat C1 F1 plus A hat C2 F2. And then what can I do next? Pull out the constant C1 A hat F1 plus C2 A hat F2. Okay, what do I know about A? So that's constant being pulled out, right? So these first two steps, simply the application of A, B, of the definition of a linear operator, right? So now, what do we do? What's A hat F1? F1 is an eigenfunction with eigenvalue equal to A1. So this is going to be equal to C1 times A1 F1, right? And this second one is going to be C2 times A2 F2. And since A1 and A2 are the same, I'm just going to call it A1 now. Okay, so I'm just going to call this A1 F2. Okay. Let's call that A2 F2. So let's do it step by step. Okay, and then you can say that C1, that's C1 A1 F1 plus C2, and I'm going to call A2 A1 now because they're the same, A1 F2. All right, so what can I do now? Multiplication is associative and commutative, right? So I can just pull out my rearrange this, and I can actually, or I can just factor out A1, right? So what do you get? A1, what's left inside? C1 F1 plus, well, what is C1 F1 plus C2 F2? That's G. And so what we did is we just proved that any linear combinations, any linear combination of degenerate eigenfunctions is also an eigenfunction, and it has the same eigenvalue. Okay? All right. If operator A is a linear operator with eigenfunctions shown on the right, A hat F1 equals to F1, A hat F2 equals to F2. So what do we notice here? They have the same eigenvalue. So F1 and F2 are degenerate. You can show that 3F1 plus 7F2 is an eigenfunction. What would be the eigenvalue? What number goes here? Also 2. Okay. So that should be a simple matter to do. You want to make that your homework? Easy homework. That's the third one. Okay. All right. So let's talk about quantum mechanical operators now. So quantum mechanical operators must be linear. So the operators that we use in quantum mechanics to represent properties, remember we said at the beginning that properties in quantum mechanics, properties, for every property of a system, there's a corresponding operator. Okay, those operators must be linear and they must be Hermitian. Okay, so the question is, we already know what a linear operator is. What's a Hermitian operator? Okay, a Hermitian operator is defined this way. Operator A is said to be a Hermitian operator if for any pair of arbitrary well-behaved functions, okay, f and g, so f and g can be any pair of functions, this integral right here must be equal to this integral, the complex conjugate of this integral on the right. Okay, let's do this step by step. This equation, just by looking at it one time, the first time, can be overwhelming. It's not really that hard. So let's do it, break it down step by step. Okay, if you operate A on function g, okay, and then that will just give you another function, right? And then you multiply that by the complex conjugate of function f. And then you integrate over all space. You should get the same answer. Well, what would this give you? That will give you a number, right? It's a definite integral. If you integrate over all space, it's a definite integral. That should give you the same result if you do it the other way. And what's the other way? You apply a hat first on f instead of g, and then you multiply it by the complex conjugate of g, okay? And then you take the complex conjugate of the result. If those two sides are equal, if both of those expressions come out to the same, regardless of what f and g are, then you say operator A is Hermitian. Okay? The Dirac bracket notation is a simple, a very simple abbreviation for this. Is to write it this way: F, A, G. Okay? And then you have your brackets right there. So we say, if you write it this way, then that means operator A on G and then multiply it by the complex conjugate of F, okay, and then integrate over all space. So this is a shortcut for that one, for this one right here. Okay, these two mean the same thing. Okay? Here's another way of looking at it. What you're really saying here is this. This is called a bracket, right? And these things are, to make it easy to remember, imagine that symbol right there. That's called, you can call that your ket operator. So what does that do to if you put a function inside the ket, inside the ket operator, all it does is it multiplies it by 1. It's an identity operator. Okay? So putting a function inside the ket operator, all you're doing to it is multiplying it by 1. It's an identity operator. So the ket operator is really an identity operator. Okay? So imagine this as a series of 3 operators. You do a ket operator on G, and then you apply operator A on G on the result. Okay? And then you apply the third operator. Our third operator here is the bra F operator. So this is the bra operator. Clever names, bra, ket. Okay? So the bra operator means this. Whatever function I have inside the bra operator, okay, take the complex conjugate of that function. And if you apply it on another function, multiply the other function you're applying it to, this result, multiply that by the complex conjugate of that function inside the bra operator, and then integrate over all space. Okay? So, let's go back up here. How would we write this in bracket notation? I have F inside the ket, right? And then I have operator A, and then I have G inside the bra. Because I'm multiplying this result right here, this A hat F, I'm multiplying it by the complex conjugate of G and then integrating over all space. So this thing on the right-hand side is G A hat F, but there's a complex conjugate outside. So this is a short way of defining a Hermitian operator. Bracket FAG is equal to the complex conjugate of bracket GAF. Okay, and there really should be a hat on that A. Now you can also show that that is in fact, this one right here on the right-hand side is the same thing as that. Okay, so these two are in fact identical. Okay, this has nothing to do with A being a Hermitian operator. What makes A a Hermitian operator is if this thing on the left is equal to that. All right, so what do we mean by A hat F G over there? When you have something like that, okay, let's call let's use another letter. Let's say F1 bracket F2. What if you don't have an operator in between? What does that mean? Okay, ket F2 means multiply F2 by 1, right? And then bra F1, since you have F1 is in the bra, complex conjugate of F1 star, and you're operating that on ket F2. So whatever the complex conjugate is of the function inside the bra, multiply it with the function that you're operating on, and then what do? Integrate over all space, so integral beta. So that's what that expression means. So if I were to write A hat F G in bracket notation, what does that mean? I'm going to write G, and then I take the complex conjugate of A hat F. Okay, you take the complex conjugate of the whole thing. Now, you cannot take a complex conjugate of the operator and the function separately. Okay, A hat F is just another function. This whole thing is just another function. Okay, we did not define the complex conjugate of an operator. So that's just going to be A hat F. So we don't do that. Okay, and then integral over all space, so integral d tau. Right? But what is that? That is multiplication. What do you know about multiplication? Commutative, right? So I can write G A hat F star d tau, right? I can do it that way. I'm just multiplying these two. But I can also say that, what is G star star? That's just G, right? The complex conjugate of the complex conjugate is the original. So G is G star star. So I can write it this way. I write the G star over here and put the star outside. Got it? Now, and then I want, instead, since I want AF star, I can just now write AF here. And then the star that goes with this AF is now out here. Okay, and then I can keep the d tau in here. D tau is just dx, dy, dz. Those are real numbers, right? So I don't have to star my d tau. So you can see that this is really, what's another way of writing this bracket notation right here? This is what? F goes here, A hat goes here, and G, since G has a star, so it goes inside the bra. But I have that extra star out there. Okay, so what I've just done is I've shown, okay, you need time to copy. What basically I've done is I've shown that this thing right here, oops, these two are identical. This is true even if A is not Hermitian. Okay? What must be true in order for A's Hermitian is for this one to be equal to that one. Okay? And in general, that's not going to be true. It's only going to be true if your operator is Hermitian. And we want Hermitian operators in quantum mechanics. Okay? So this is the Dirac bracket notation for writing integrals. Okay? Prove that operator A is as defined below is not Hermitian. Okay, let's start with a simple example. Okay. Let's prove that the identity operator is Hermitian. Okay? So let's do this. We'll do that one later. So let's say we prove that E hat F is, if E hat F is equal to F, so E is identity operator, prove that E hat is Hermitian. Okay. What do I need to prove? F, E, G must be equal to what? G, E, F star. Okay? So to prove something is Hermitian, switch and then star. Okay? Switch the functions and then take the star. If you get the same result, regardless, then your operator is Hermitian. So how do we prove that? Well, let's write this in standard form. Integral of F star E hat G d tau, right? And what do we do next? And this, what is this integral? Integral of G star E hat F d tau, and I have to take the complex conjugate of that. Right? I have to show those two to be equal. Let's pause for a minute. Let's continue. So, what do we do? What does E hat G do? What does E hat do to G? It's an identity operator, right? So this is going to be integral of F star G d tau. Got it? And I want my f to be what? To have no star, right? Or do I? Okay. Let's just. I want my e now to go with my f instead of going with my g, right? So what do I need? What do I need to do? So I'm gonna say I'm gonna pull out the star. I don't want my f to have a star here, right? And I want it to go with my e. So I'm gonna pull out the star. So this is gonna be integral of f g star d tau star. You still with me? Okay. F star, and then g star star is g. Because all a star does is, all that does is anytime you see an I, you replace by negative I. And I is just a constant. So wherever your I shows up, you just replace by negative I when you put a star. D tau you don't have to star because x, y, and z are real coordinates. Okay, so you don't need to star your d tau. Okay, but f and g you'll have to explicitly star them because you don't know what they depend on. You know they depend on the coordinates, but you don't know the actual expression for the function. There might be an I somewhere in the function.
What is it?
E hat, we define it as an identity operator. All it does is it multiplies the function by 1. Okay? All right, so what do we do now? Well, what is f hat? It's the same thing as e hat, right? F is just e hat times f, right? If I do e hat times f, it's still f. So that's e hat f, and then that's g star d tau integral, and then the whole thing is star. What do I get now? This is integral of 1. E hat f star. Oh no, let me switch them around. Okay. I'm going to put the g star over here on the left. G star. E hat f d tau. And I still have that star on the outside. Right? But that's what this is, right? That's the same. Okay? So basically, what are we saying then? That the identity operator is a linear operator. So in other words, when we say something like f hat fg in a bracket, if I switch g and f, what do I get? I just have to put a complex conjugate sign there. Then those two would be equal. Okay? If you switch two functions in a bracket where there's no operator in between, you can switch those two functions. Just make sure you put that star on the outside, because that's what basically this is. Because this basically is what? This is just g, right? So f star g, and that's g star f. So this expression right here basically says that the identity operator is a Hermitian operator. So if I were to ask you, what's the integral of, okay, if I say integral of, let's say, f1 star f2 d tau, okay, is that equal to integral of f2 star f1 d tau? No. What would make them equal?
A bracket.
I need to put star. When I switch two functions, I have to put a star. Okay. Now, if there's if there's an operator between them, and I can still do that, putting a star makes them equal, then you say that that operator is a Hermitian operator. In fact, here it's the identity operator that's implied to be a Hermitian operator, right? So, is it time to go?
Yes.
Okay, so next time we're going to prove that this operator right here is a Hermitian operator.